Namaste, hello everyone, welcome to this session. So in this session we are going to solve some examples on the topics we covered in lectures 14 to 17 of this course on experimental model analysis. The topics we covered in these lectures are Fourier series expansion, Fourier transform, then discrete Fourier series abbreviated as DFS, and then discrete Fourier transform abbreviated as DFT, and then DTFT, that is discrete time Fourier transform, and FFT, which is fast Fourier transform. So we have studied all these things in those lectures. You would see that these topics essentially are on the signal processing as required for model analysis and testing, and they require a lot of data processing, and that is why it is difficult to have classroom like numerical problems based on manual calculations. Still I have designed some problems to reinforce the understanding of those concepts, and those examples we are going to solve in this session today. So please watch the lectures for the relevant background theory of signal processing. Of course, we are going to have another couple of lectures in the next week also dealing with signal processing. You would also see that I have designed many multiple choice questions to test the basic concepts we learnt in the lecture classes, and they are part of the assignments on these topics, right. So of course you need to carefully go through the lectures in order to solve those problems, right, as they are based on some important concepts in those lectures. Okay. So I think let us get started with the examples in this session. So let us start with example number 1. So this example is about use of Fourier series expansion. So in practice we may encounter systems where the forces which are acting, they are periodic in nature, correct, and such periodic forces, when they are acting, we do not have a closed form solution to find the response of the system, correct, but we do have expressions for the closed form solution if the forces are harmonic, right. So therefore what we do is that these periodic forces then we can represent as sum or sum of harmonic forces using Fourier series expansion, right, and then we can then deal with each of the harmonic component making up the periodic force using the standard expression we have developed in the theory classes, right. So each harmonic component of the periodic force then can be dealt in this manner, and a response can be found out for each harmonic component, and then response due to all those harmonic components can be superimposed to obtain the response due to the periodic force. So this is basically going to be the scheme or strategy to solve this problem. So let me formally write down the question, right. So figure shows a periodic force acting on a single degree of freedom system with viscous damping. The parameters of the system are: mass is given as 2 kg, then K is given as 493 Newton per meter, and C, the viscous damping coefficient, is given as 5.65 Newton second per meter. Find the steady state displacement amplitude of the response, right, based on first three harmonic components, right. So, the force that is given is something like this. This is the periodic force and it is in the form of a triangular wave. It is in the form of a triangular wave like this. Something like this, right. And the values are, this is the highest amplitude, this is 10 newtons, right, and this time is 0.1 seconds, this time is 0.05 seconds, this time is in seconds and force is in newtons. So, this is what has been given, right. So, let us try to see how we can solve this problem. So, let us start with the solution. So, as I explained, our strategy will be to use Fourier series expansion. So, let me formally just write down what strategy we are going to follow or the steps in the solution, right. So, the first step will be to do Fourier series expansion of f of t, correct, that will be the first step. Then solve for the response due to each harmonic component, right, making up f of t, right. That is the step 2, and then 3 algebraically sum the responses due to first 3 harmonic components, because that has been specified in our problem, due to first 3 components, and then from that we can determine the maximum value of the response, that will be the amplitude. Find the displacement amplitude. So, these are going to be the steps. So, this essentially gives you the bird's eye view of the solution process. Also, one thing I would mention here is that we have been asked to find steady state displacement amplitude, which means that the transient part we have to ignore, because whenever the force acts there would be an initially a transient present in the response, transient response, and because of the damping that part of the response would gradually die out, and then after that time only the steady state part, which is the due to the force being applied, will be left out. So, we are supposed to ignore the steady transient part and only find the steady state displacement amplitude. So, let us now start with the process of Fourier series expansion. So, the first thing we can note here is that this force is periodic, right, this force is periodic, f of t is periodic, and for periodic forces or periodic signals we can use Fourier series expansion, right. So, therefore, Fourier series expansion can be carried out, right. As we studied in the lectures, if it is not periodic, then it will be an aperiodic signal, and then we cannot do Fourier series expansion, and in that case we will have to do what we call as the Fourier transformation, right. Of course, here we are going to use the Fourier series expansion. So, what is the time period now? Let us say time period and let us designate it by T naught. This T naught is, as we can see from the figure, it is 0.1 second. After 0.1 second the signal repeats, right. So, this is nothing but the time period T naught, right. And now what is the fundamental frequency? Fundamental frequency that would represent by omega naught, and that will be equal to 2 pi upon T naught. That will be the fundamental frequency, correct. Of course, in the hertz, if you want to find out, then this will be basically omega naught upon 2 pi, that will be in hertz, and this is in radians per second. So, now we do the Fourier series expansion. So, let us go to next page, and we have studied that the Fourier series expansion is given by Fourier series expansion can be written as f of e, right, is equal to a naught plus a r cos r omega naught t with r varying from 1 to infinity, right, plus b r sin r omega naught t with r varying from 1 to infinity, correct. So, that is the Fourier series expansion. So, a naught is the DC component and a r is the coefficient of the cos components, harmonic components, and b r is the coefficient of the sine components. So, now how do you find a naught? Of course, before that we will have to first express f of t as function of time, right. So, let us do that first. Let us express f of t. We can see from the figure that maybe let me again draw that figure here, f t, right. And so, this is the so signal is, if I look at the one period of the signal, if I look at the one period, then this is like this, right. This is t naught and this is 0.1 second and this is 0.05 second, correct. So, it means the signal essentially for 0 to 0.05 there will be one equation for f of t, and from 0.05 to 1.1 second there is another equation, correct. So, it means that and what is the slope of this line? If I look at this line, the slope of this line is, because we know that this quantity is 10, right. So, it means the slope of this line is equal to essentially 10 upon 0.05, which is 200, correct. That will be 1000 by 5, that is 200. So, therefore, this equation of this line would be, as we know that equation of line is simply given by f is equal to slope t plus c, that is the equation of line, f is equal to mt plus c, and in the present case the slope is 200. So, 200 t and the intercept of this line is 0 because it passes through origin, correct. So, it means the equation of this line is essentially f is equal to 2t. Similarly, if I look at the this one, this line which is there from 0.05 to t, then this line again what is the slope of this line? That is minus of the slope of the line in the first part, that is minus 200, correct. So, if I look at this line now, this line, the slope is minus 200, and what is the intercept on the y axis? Intercept on the y axis will be around, it will be around 20, right. By using the properties of the triangle I can say that it is 20. So, this is 20, and therefore, the equation of this line would be f, again I apply the same equation mt plus c. Slope is now minus 200 t and the intercept is 20. So the equation of line is f is equal to minus 200 t plus 20. So now we are in a position to write the equation of line. So therefore we can write the equation or the expression for f of t. So we can say that f of t is equal to 200 t, right, for t greater than or equal to 0 and less than or equal to 0.05, and it is equal to minus 200 t plus 20, right, for t more than or equal to 0.05 and less than or equal to 0.1. So this essentially constitutes the definition of the forcing function, right. So once this forcing function is there, now we can find out using the techniques we learnt in the lecture class, that how do you find these coefficients a naught, ar and tr, that we have to determine. So let us now start with that. So how do you find, let us say, coefficient a naught? How to find? Right. So a naught is essentially called as DC component, or it also represents the average value of the signal. And we learnt in the lecture classes that a naught is essentially equal to 1 upon t naught integration from 0 to t naught f of t into dt, which is nothing but the average value of the signal, right. So if you substitute f of t, then you get t naught 0, and we will have to break this integral into two parts now, from 0 to t by 2 t naught by 2, correct, f of t into dt plus t naught by 2 to t naught f t into dt, correct. So now we can substitute this here, that will give us t naught by 2 to 0, that is 200 t into dt plus 1 upon t naught by 2 to t naught and minus 200 t plus 20 into dt. So I think this is very easy to carry out, integration of t, and t will be t square by 2, and we can do all that stuff, apply the limits. So let me write the final result now. After doing the integration and applying the limits, we get a naught as 5.0, correct. That is the DC component or the average value of the signal, and it is also in fact can be easily verified by looking at the the time domain forcing function. If you look at the the first time period, then the average value of that is nothing but 5, correct. If you try to imagine a rectangle whose height is such that the area of the rectangle is equal to area of the triangle in the first from 0 to t naught. So that height of the triangle will be essentially 5. So therefore it very well matches with the our observation as well. So now next thing would be to find the components AR. Okay, so let us go to next page. So AR would be now let us component find AR, right. So now AR is given by this, we have derived in the lecture classes the expression AR is equal to 2 by t naught integration from 0 to t naught f of t cos r omega naught t dt, correct. And this integral also we will have to break into two parts, first from 0 to t naught by 2, correct. So here we are going to say 200 t into cos r omega naught t into dt, correct, plus integration from t naught by 2 to t naught, right, and here you are going to have minus 200 t plus 20 cos r omega naught t dt, right. So let us I think we will perform this integral so that you know exactly how whole process goes, right. So let us divide this integral into two, let us represent them as a r. Let us call the first integral as a r1 and second as a r2, right, and we will solve them one by one. So let us first find the integral a r1, which is equal to 2 upon t naught, right. I can take out 200 outside, 200 outside, 2 into 200, right. Then I have integration from 0 to t naught by 2 and then t cos r omega naught t dt, correct. That is what we have, and now we can write this as 400 by t naught, and now I can use the first because t into cos r omega naught t, I do not know the direct expression for the integral of this quantity, it is product of two functions. So I can use integration by parts. So maybe I can write here using integration by parts, then I have for this first function, right, p integration of second function, that is cos r omega naught t dt, correct. So this is the t naught by 2 to 0, right, and then I have minus integration of differentiation of the first function, right, first function is t, into integration of the second. So that is nothing but cos r omega naught t dt, correct. So this is the basically application of integration by parts. So next then I can perform this integration. So I get 400 by t naught, then t integration of this is sin r omega naught t upon r omega naught, right, and then limits from 0 to t naught by 2, correct, and then I have minus integration 1 and then integration of this is sin r cos omega naught t upon r omega naught into dt. So I think here I have once more dt, right, because there are two integrations. So this is where we reach. Then after this now we can further go ahead like this. Now we get 400 by d naught, right, and then I can apply the limits for this. So I get t naught by 2 sin r omega naught t naught by 2 divided by r omega naught, right, and then minus 0, correct. So that is the first term. So the second part would be minus the integration of sin r cos omega t is minus cos r omega naught t divided by now r omega naught square, right, and then limits would be, right, that is the limits. So therefore now if you write this further, then what is going to happen? So this would be, you will have 400 by t naught, right, and then you have here t naught by 2 r omega naught sin. Now omega naught can be written as 2 pi upon t naught, right. So therefore we get sin r pi, that is what we get here, right. 2 and 2 cancels out, T naught and T naught cancels, sin r pi, and then of course 0 is there, and then we have plus cos r, right. Here also we will have cos r pi, right, and then 0 cos r naught, cos r omega naught 0 would be 0 1, right. So, therefore, minus 1 and then divided by r square omega naught square, that is what we get, correct. And then we know that since sin r pi is 0, right, for r 1 2 all integers it is 0. So, therefore, we end up with this result, that a r I, right, first part is 400 upon T naught r square omega naught square cos pi r minus 1. So, this is the first integral, correct. Let us go to next page and evaluate the second integral. So, the second integral would be now integral AR2, right. This AR2 would be essentially 2 upon T naught from T naught by 2 to T naught minus 200 T plus 20, right, cos r omega naught T dt, correct. So, this also now you can proceed in the same manner, correct. You can proceed in the same manner, perform integration by parts, right, and then you can easily get this result, right, which I am going to write now. AR2, this would be minus 400 upon T naught r square omega naught square cos 2 pi r minus cos pi r. So, this is the result for the second integral, and then now we can obtain the complete integral A r is equal to now A r 1 and then A r 2, and if I substitute this here, what I am going to have is, the first one is 400 upon T naught r square omega naught square, I can take as common, right, and then inside I get cos pi r minus 1 from the first part, and then I get minus cos 2 pi r cos 2 pi r, right, minus cos pi r from the second, right. And what we note is that this cos 2 pi r, note that cos 2 pi r is always 1, cos 2 pi r is always 1, because if I take r is equal to 1, it is cos 2 pi, if I take it is cos 4 pi, cos 6 pi, so all that will be equal to 1, so that is 1, and then the result we get is 400 upon P naught r square omega naught square into bracket 2 cos pi r minus 2, that is what we get, right. And now, so this essentially becomes 800 upon T naught r square omega square cos pi r minus 1, right. And what is this quantity? If I look at 800 upon T naught r square omega naught square, this is essentially 800 upon T naught is 0.1, or maybe we can first simplify and then substitute T naught r square, this is 4 pi square, right, into T naught square. We can substitute 2 pi upon T naught in place of omega naught. So, this gives me 200 T naught upon r square pi square, and because T naught is 0.1, so essentially you get this as 20 upon pi square r square. So therefore we can finally write down AR is 20 pi square r square cos pi r minus 1. This is the result for AR, right? And also we note that if R is if we take R is even, then if R is even, then cos pi r, right, then cos pi r will be equal to 1, and that would make AR as 0. And if R is odd, correct, if R is odd, then we have cos pi r as minus 1, and that makes AR as minus 40 upon pi square r square. So let us now determine the value of BR. If you look at now BR, let us find BR. So BR is given by 2 upon T naught 0 to T naught x of f of t into sin r omega naught t dt. Okay. And now we can go through the similar process as we did for AR, and the result would be that you would find that BR is actually 0 for all r. You would find that BR is 0 for all values of r. So the reason is that if you look at the function which has been given to us, this function is like this, right, and if you try to also sketch it on the negative side, then it will be like this. So this function is essentially an even function. It is an f of t is an even function, which means that f of t is equal to f of minus t. So it is mirror image about the vertical axis, about the y axis, that is why it is an even function. And if you look at the sine function, if you look at the sine function, any sine function like this, so sine function is not an even function, it is an odd function, right. Sine r omega naught t is an odd function, because sine r omega naught t is not equal to sine r omega naught minus t, correct. And that is why we see that BR components are not required to make up the periodic function f of t, and that is why the integration process has led to the result that BR is 0. And the cost functions are even functions, okay. The cost functions are cos r omega naught t is an even function, since cos r omega naught t is equal to cos r is equal to cos r omega naught minus t, right. And that is why we see that the coefficients AR, they have not turned out to be 0, all of them, they are there which are non-zero. So it means those components, cost components, are required to represent or break this periodic function as sum of harmonic functions. So with this result now we proceed further. So once we have got it, now we can write the Fourier series expansion as we obtain. Therefore we have f of t is, we can write as a naught, which is phi plus r varying from 1 to infinity the IR components. This is minus 40 upon pi square r square, right, cos r omega naught t. So, this becomes the Fourier series expansion of f of t. Now, we see that on the right hand side we have the harmonic components, and now we know from our theory of single degree of freedom system that if there is a harmonic force acting, then what is the response, correct. So, we know that from our single degree of freedom analysis. So, therefore, we can easily determine now the if we focus our attention on one of the harmonics, then we can determine the response due to that. But before we do that, let us first of all maybe what I can do is that I can first discuss that if I have a particular harmonic component, let us say f r, right. If I have a particular harmonic component, let us say rth component of force which is f, I can call as f r t, and that is given by f r 0 cos r omega naught t, right. How to find response to that? So, we know that the frequency response function is given by alpha omega, the receptance FRF, which is given by 1 upon k minus m omega square I omega c, correct. And the magnitude of the this I can determine, and I can also determine the angle of the phase of alpha omega is equal to tan inverse omega c upon k minus m omega square, correct. So, therefore, now the response would be response to FRT. What would that be? That would be given by XRT, right, is equal to XRT would be equal to the magnitude of the frequency response function at that frequency, right, multiplied by, so maybe I can write it as, because the frequency here of the force is r omega naught. So, at that frequency you have to take the magnitude, right, and then we need to multiply it with the magnitude of the forcing function amplitude f r naught, right, and then the phase. So, r omega naught t minus whatever phase we get, let us call it phi. So, this phi is actually this phi. So, that gives us the expression for the XRT, right. So, therefore, now we can work out all these numbers for all the components, and let me write those results on the right hand side. So, what I am going to do here is I am going to write the frequency, that is excitation frequency omega, correct, and what that excitation frequency is, first is 0, that is the DC component, and then you have r omega naught. So, for r is equal to 1, so here r is equal to 1, that is the r is equal to 1, that is omega naught, and that omega naught is 62.8, that is what we get, right. If you find omega naught, then that value is given by 2 pi upon 0.1, right, that is 20 pi, which is 62.8 radians per second, and then I have r is equal to 2, which is 1, then I have 188.4, and then r is equal to 3, okay. So, this is actually r is equal to 3, because the even component is 0. So, r is equal to 3, and then r is equal to 5. So, that becomes 314.15. So, first three components we are going to have, okay, like this, and then what is the F R naught, the amplitude of the force, this is 5.0 for DC component, and then I can work out the value of the minus 40 upon pi r square for different values of r, and those are minus 4.05 minus 0.45 minus 0.16. Then I can work out the value of the magnitude of the frequency response function at the frequency of excitation, right. That value for the DC component is simply 0.002. This is 0.1349 into 10 to the power minus 3, 0.0142 into 10 to the power minus 3, 0.0051 10 to the power minus 3, right. And then you can determine the value of the amplitude of the displacement due to this component. So, that I can call as x r naught, and that turns out to be point. So, this x r naught is actually this product x r naught 0.0101 minus 0.5469 into 10 to the power minus 3, then minus 0.0064 into 10 to the power minus 3, and then minus 0.0008 into 10 to the power minus 3. That is what we get. And then I can determine the phase angle phi, right. This is 0 degree here, and then 177.2 degree, 179.13 degree, and then 179.4 degree. So, this is what we get, all the data, correct. And then if you combine all of them, so what is going to happen is that we are going to have the expression x of t, which is actually equal to the you sum all these components, right. So maybe I can write here as r is equal to 1 to 3. So in this case we are going to use value of r is 3 and 5, correct, 3 values, and then I can write here x r naught cos r omega naught t minus phi, that also I can add r here, phi r, correct, because it is for the particular component, and plus the static component x static, right, which is the r is equal to 0. So if I combine all this, I get the resultant displacement of the response of the system, and then I can determine the maximum value of this x of t. So the maximum x that is found as 0.0107 meter, something like this, okay, that is the maximum displacement. So in fact, if you like plot this, then the response may look something like this. If you plot this x of t, then that response may look like this. So there is a significant DC component, as you see from the table. The x is 0.0101, right, this is the DC component. So therefore there is some DC component, and over that DC component you are having variable components like this, which are due to the first, third and fifth harmonic. So I think this fairly demonstrates that how we can find the response of a system if periodic forces are acting, by employing Fourier series to expand the periodic force into harmonic components, and then analyzing different components individually and then adding them. And most important thing to understand is that this process is something possible only because of the fact that system is linear. We are assuming a linear system, and hence this superimposition, finding the response by superimposing the response of individual forces, that can be done and allowed only if system is linear, right, and hence that could be done, right. So, I think in this way we complete first example. Let us go to the next example. Let us go to next page. Example 2. So, let me write the question first. Question: a signal with a frequency range of 0 to 1600 hertz is to be measured. A record length of 4 seconds is used or measured. Find the time and frequency domain parameters of the measurement. Solution. So, let me tell you some little background we have studied in the lecture. So, as we study in the lecture, there are measurement parameters related with the time and frequency domain, right. So, if you look at the time domain, then the background theory, right. So, if you look at the time domain, then the time domain signal will have a discrete signal like this, correct. If I am taking discretization, then this is the signal, right, and then so this is the discrete time signal, correct. And here therefore, this resolution, time resolution is called delta t, correct, and then we have the record length. So, this is the record length t. Of course, we have signal here also like this till here. So, this is the record length, and then we have in the frequency domain we have the spectrum like this, correct. So, in the frequency domain, this is the frequency domain representation, right. So, here we have the resolution of the spectrum, where the frequency resolution is called delta f, right, and then we have the maximum frequency range, correct, like this. So, therefore, there are different parameters. So, if I now list here those parameters, the time domain parameters are we have the time domain parameters. For example, the first parameter is what is the time domain resolution, or what is the time step delta t. Then we have the second parameter as what is the record length t. Then we have how many samples are there in the time domain, correct, nt is the number of samples in the time domain. Similarly, we have the frequency domain parameters. So, that parameter maybe we can call as the fourth parameter, that is the frequency resolution delta f. Then we have the frequency range, that is f max, 0 to f max. Then we have the sampling frequency fs, and then we have the number of frequency components nf. How many frequency components are there? So, you can see there are so many, these all 7 parameters are there, okay. And we have studied or learnt in the theory classes that only 2 of these parameters can be chosen independently, and the rest of the parameters they are related to those 2 parameters, correct. So, in this example what has been done is that we have been given 2 parameters of these out of these 7 parameters, and we have been asked to find the remaining time domain parameters. So, this is basically the description of the measurement process of the in the time and frequency domain. When we measure a time domain signal, we have analyzers which discretize the signal, and then they perform Fourier transform, that again is discrete, correct. So, therefore, as a engineer doing this measurement, we must be fully aware that how these different parameters are related. So, this question basically I have designed just to enforce that and reinforce that understanding. So let us see that what has been given to us. So, what has been given to us is f max. We have been given f max as 1600 hertz, that has been given to us, correct, and then the record length is given as 4 seconds, correct. So, this is given to us. So, now we are going to find out the remaining quantities. We are going to now find. So, the first thing would be you have like sampling frequency fs, and we studied that the because here the measurement frequency range has already been given. So, then we can choose the sampling frequency by satisfying the Nyquist theorem, which says that the sampling frequency must be twice or more than the maximum frequency range, correct. So, that is why we are going to take the sampling frequency as twice of f max, and that would be then 3600 hertz. Then we have the frequency resolution delta f, and we know that it is actually equal to 1 upon the record length, that record length determines the frequency resolution. So, this is now 0.25 hertz, 1 upon 4 is 0.25 hertz. Then the time step or time resolution delta t, right, let me rewrite this delta t, that is essentially that depends on the sampling frequency. So, 1 upon fs, and therefore, that would be 0.00033125 seconds, right. And then the number of time samples depend upon what is the record length and what is the time gap, correct. So, t upon delta t, and that will be 12,800 samples, and then the number of frequency lines nf, correct. So, that depends on what is the frequency range and what is the frequency resolution. So, f max upon delta f, and that gives me 1600 upon delta f, which is 0.25. So, I get 6400. So, it will be 6400 number of frequency lines, correct. So, I think this basically solves the problem, right. But just one thing I would like to mention here is that here the frequency range was specified, and hence it was indirectly given that there are no frequency components beyond 1600 hertz, correct. But we will see later that also when we do not know the highest frequency component present, we will have to first use an anti-aliasing filter, right, and that of course we will study in a later session, right, and we will solve a problem based on that. Okay. Let us go to problem 3 now. So, now we are going to hold a problem 3 and problem 4, right, example 3 and example 4, they are based on MATLAB codes. So, we have to write MATLAB codes and solve them. So, let me describe the example first. So, example 4. Question: write a MATLAB code to find the DFT, that is the discrete Fourier transform, right? Discrete Fourier transform of the signal given below. Use a record length of 1 second and a sampling frequency of 30 hertz. Also find one-sided DFT, right, and plot continuous signal, discrete signal, and magnitude magnitude of complex, that is two-sided DFT and one-sided DFT. So, you have to plot these results as well. And what is the signal given? X of t is equal to 4 sine 2 pi f t plus 12 cos 2 pi tan t. So, this is the signal. So, I think before we start writing the program and see that how that works, let me tell you a little of background which is required to understand the program. Of course, these are all things explained in great detail in the lecture classes, and you are supposed to look at that before you go through these examples. But just for the benefit of all, I am giving you a summary of the relevant background. So, summary of relevant background, right. So, we derived an expression for discrete Fourier transform related to also DFS, right. So, I am going to write that expression because that is what we are going to use in the program. So, that expression is xk, right, is equal to 1 by n xn to the power minus I k 2 pi by capital N into small n, with n varying from 0 to n minus 1. So, this is the expression for basically discrete Fourier transform or discrete Fourier series also we can say, right, which we are going to use. So, here the k varies from, here k, this expression has to be used from 0, 1, 2 up to n minus 1, right. So, here k is the index of the frequency, right, frequency line. K is the index of the frequency line, right, and n is the index of sample number, index of time domain sample. So, we see here that the I think I need to correct this starts from 0, right, starts from n is equal to 0 to n minus 1, right. So, now one thing we should I would like to mention here is that here the k is varying from 0 to n minus 1. Now, in the program we will have to use a for loop to vary this number, and an array which can store the magnitude of the this frequency component we need to have. Now, that index cannot start from 0, it has to start from 1, right, because the index cannot have a 0 value, right, it has to start from 1 2 3 4 like this, right, in tree. So, therefore, we will have to use the appropriate index, a compensation of 1 there. So, that is what we will do. So, instead of k varying from 0 to n minus 1, we will make it vary from 1 to n. Similarly, so let me say that therefore, the k we will use the variation from 1 to n instead of 0 to n minus 1, correct. And similarly, so varies in the code from 1 to n. Similarly, if you look at the n in the formula, you can see it varies from 0 to n minus 1, but that also index, it has that the sample vector xn is the first element will be referred with index 1, not 0, and therefore, this also varies in the code from 1 to n, not from 0 to n minus. The other thing is that the DFT frequencies, the frequencies, as we discussed in the lectures, we can have the complex frequencies I think varying from 0, 1, the index we can have like 0, 1 or up to n minus 1, n number of frequency components, which of course in the program we are going to use from 1 to n, right. So, this is like having the frequency components, complex frequency components as 0, then delta f, then 2 delta f, and going up to n minus 1 delta f like this. And the alternative way is to have it on both sides. So, I can have minus n by 2 into delta f like this, then 0, then I can have delta f, and then 2 delta f, and then up to n by 2 minus 1 into delta f. So, you have negative frequency axis and you have positive frequency axis. I can have such two-sided spectrum, means on both sides I can have, and the same thing what I can do, I can translate this and show it completely on the positive side as shown in the top figure, correct. So, what I am going to do is in the code I am going to use the frequency components which are half of them on the with the negative indices or negative frequencies, and half on the positive side, correct. So, that is what we are going to do. So, the next question we are going to have is question this is example. So, this is actually example 3 rather, let me make that correction here, this is example 3 and this is example 4. Okay. So, in this example we have to solve example solve the previous question by using MATLAB FFT command, correct. So, in this example we are not going to use our own code for DFT, but we are going to use inbuilt MATLAB FFT command, correct. So, let us now go to the MATLAB platform and okay. So, you can see this is the first program which I have written, right, for the example 3, where we have to find DFT of a signal. Let me explain you all the steps. So, this of course I have explained you in the previous session that this is to clear all the MATLAB workspace variables. CLC is used to clear the all the data which might be there on the command prompt, on the command window. We just clear that command window. With close all, we close any existing figures which might be there, right. Then now we define record length, because it is given to us in the problem that the record length should be 1. So, we have taken t as 1 second, then we choose the sampling frequency, which also already given in the example as 30 hertz, and then we have now we are finding the time step, right, the resolution, time resolution delta t, and that is 1 upon fs. Then we are going to build a vector of time now, because we have to also plot the signal and then compute DFT. For that, time vector would be required, right. So, t vac we start from 0 and then we increment it by delta t, and the ending time is the t minus delta t, right. So, t is the record length and then the minus delta t. So, that is the last sample we have. And then the number, then we find the number of samples n, which is the length of the t vac. So, whatever is the length of t vac, those would be the number of samples, that is n. Now we find the frequency domain parameters. So, which is the frequency resolution delta f, that is equal to 1 upon the record length. Then we have the maximum frequency range, or the range of Fourier spectrum, or the DFT we are going to have f max, that is fs by 2, correct. So, these are the time and frequency domain parameters. Now we are going to find a discrete time signal. So, in the example we have been given the continuous time signal in terms of variable t. Now we have to find a discrete signal. So, what we do, you can see this is the same signal we have written down, but in place of t we are just writing t vac. Now t vac is not a single time instant, but it is a collection of all the time instants making up the discrete signal, right. So, that is t vac, and then and you can see in the cost term also we have substituted t vac. Rest of the things are same as given in the example. So, what happens now with this statement, x would be a time vector. It will be basically a vector containing all the samples of x at all the different instants of time, correct, based on which has been decided based on the sampling frequency. So, x is a vector of samples of the signal. Now we are going to write the code for DFT. So, you can see here now I have written this code. This is the code for DFT, right. So, so here we are going to find DFT from minus n by 2 to n by 2 plus 1 frequency lines, as I explained just now, that we are going to have half frequency components on the negative side and the remaining half on the positive side, correct. So, therefore we start with, so k is now the index of frequency from 1 to n. As I said, we cannot start from 0, because here the MATLAB does not allow having 0th element as the first element. The first element is always numbered as 1. So, we have to start k from 1 to n, right. Then we say we have to sum the elements. So, we say sum the all values. So, sum is equal to 0, and as I said in the frequency again we want to have frequency components on the negative side starting from minus n by 2. So, that is why I am subtracting from k minus n by 2. So, that we kk is a dummy value of k, and then we are having the sample again varying from 1 to n, because we cannot do from 0 to n. So, in the formula you can see we do an appropriate adjustment. So, I am writing here sum is equal to sum plus x n e to the power minus I into kk minus 1 into e to the power into 2 pi n minus 1 upon n. So, you can notice that what I have done is if you look at this part, this is nothing but the right hand side of the formula I wrote earlier, right. And here in place of n I have substituted n minus 1, because our for loop is starting from not from 0 but from 1. So, in order to make that compensation I am subtracting 1. Similarly, wherever kk is there I am subtracting again 1 from that, correct, because the k is starting from 1 to n. So, that compensation for 1 has to be done, because in the actual formula k is from 0 to n, right. And of course, instead of k I am using kk, because I want to have frequencies starting from the negative value from minus n by 2, not from 0, correct. So, this, and then of course, sum is equal to sum plus something, means it will calculate this value of this expression for n is equal to 1 and then store it, right, and then add it to the existing value of sum, which is 0, and then call that new sum new value as the new value of the sum, and then it will keep on repeating. So, it is going to accumulate the value of this expression in the variable sum, right, and then at the end what happens, we have to divide it by n as per the formula. So, we are then, once the sum is done, we divide this by n, and that becomes the magnitude of the kth frequency component, correct. So, this completes the DFT program, right. Then the next thing is now that we want to also plot this spectrum. So, we need to find the frequency vector, that is what I am going to do next. You can see here in this I am finding the frequency vector to plot DFT, and now the frequency vector, it starts from minus value, minus, you can see minus f max, that is minus fs by 2, and the increment is delta f, which is the frequency resolution, and it goes up to f max minus delta f, right. So, that is the last frequency component. So, this f vec CMPLX essentially a vector of frequencies, and I have called it CMPLX, that is the complex, because we are going to have a complex DFT, which means that it has the half frequency range on the positive negative side and the half frequency range on the positive side, correct. So, it is a complex DFT, it is symmetric with respect to, magnitude is symmetric with respect to the y axis. Now, we are going to plot these values. So, of course, before that we need to convert, because as has been asked in the question, we also need to find a single sided DFT, right. So, I am now converting here, which also I explained in the lecture classes, that how to convert from two side to double side, right. So, you can see we are basically, first of all the first component is essentially the x k n plus 2 plus 1, and then the other components are the twice of the complex frequency components, right, and then the last frequency component is this one, correct. So, this yk therefore gives us the single sided DFT, and then we also need to find single sided frequency vector, and that will start from 0 with a frequency resolution delta f and going up to f max. So, this essentially is the stage is now ready to make all the plots we obtain. Now, we are going to draw the figures. Now, to draw the we also have to draw the continuous signal. So, we obtained the discrete signal, right, for DFT, but to plot this continuous signal, what I am going to do is sample the signal at a very high frequency, so that when we plot it, it would look just like a continuous signal, because the with a high sampling frequency the samples will be very closely spaced, right. So, that would give us a basically visible effect of having a continuous signal. So, you can see here I am basically, this is the same program I have used for discretization earlier. I am using a high sampling frequency 256, and then of course I am finding the delta t for that high frequency sampling frequency, then finding the time vector for that, and then finding the discrete signal based on this high sampling frequency. So, these statements are same which we used previously to sample the signal. So, this basically uses a samples which have been developed obtained using high sampling frequency. Now, we are first plotting the time signal. You can see the figure announces develop a new figure plot. Now, I am plotting here the signal sampled with high sampling frequency. So, t vac high is the vector of the samples, x high is the the samples. So, this will give us it will now all join all the points by lines, and then it will give us a field of a continuous signal. So, this essentially plots the original time signal. And now hold on, means I want to have an overlay. So, on the same plot I am going to plot the signal for which we are finding the DFT, right, which was sampled with sampling frequency 30 hertz. So, I am using here now a stem plot, so that I can see that signal as a sampled signal, right, stem plot, and I am using the T-VEC as the time vector, x is the signal which we had discretized to find DFT. So, this basically will going to overlay the discrete signal over the continuous signal. So, these of course some other statements to plot the label on the x axis, label on the y axis, title of that plot, setting the fonts and other things. These are all not necessary in the things. This font and all this, you can skip this if you do not want. Now I am plotting the, say again plotting the discrete time signal just to have a separate copy of that. This is same, I am just plotting the new, I am making a new figure with the stem plot of the discrete signal. Then after this I am plotting the two sided DFT, you can see here two sided DFT I am plotting, complex DFT, announcing a new figure, and now I am plotting the a stem plot with the on the x axis we have the complex frequency axis f-VEC complex, and then we have the on the y axis the magnitude or the absolute value of the frequency component, right, magnitude of the frequency component xk, capital Xk. Rest of these things are all like labels and titles and font sizes and all those things, color. Then I am plotting the single sided DFT, you can see here, again announcing a new figure and making a stem plot. Now this time using f-VEC real, that is the real frequency vector, and then absolute value of the single sided DFT frequency component magnitude, absolute value of yk, right. So I think this basically how I have developed the program. Now let us run this program to see that what kind of output we are getting. So let me hit the button run. I am now pressing the button run. So it is running, you can see it is busy, it is showing the message, and very shortly you can see it has done the computation. Now it is drawing the figure, and let us look at the first figure, right. This is the first figure. So here what we see now, as you remember we had plotted a overlay of the continuous signal. So the blue one is the continuous signal, which is the x of t which we wanted to analyze, and we use a sampling frequency of 30 Hz to discretize it. So this red one, the stem signal is a discrete signal we have recorded. So red all samples are the recorded components, blue is the actual signal which was there, right. So there is the discrete signal. Then we have you can see this figure 2 shows the only discrete signal, so that we have a very clear idea of what is the discrete signal we have recorded. So you can see by looking at this signal it is not very clear what kind of signal it is, right. But then we are going to do a frequency domain analysis DFT which will tell us what are the frequency components present in this signal, right. So let me show you figure 3 now, which will show us the complex DFT. So this is the complex DFT, you can see it is two sided magnitude plot, and on the x axis you see it starts from minus fs by 2, so that is 30 Hz. So fs by 2 is 15 Hz, so minus 15 Hz, and it goes up to 14 Hz, which is 1 Hz less than the one line less than the 15 Hz, right, minus, that is n by 2 minus 1. So you can see all the components are there, it starts from minus 15 Hz and go up to 14 Hz, right, and you can see it is symmetric. So we have the negative frequency axis from minus 15 Hz to 0, and from 0 to 14, it is symmetric with respect to the y axis. And what also we note that if you remember the signal that was given, it had two frequency components, one was at 5 Hz and other was at 10 Hz, and very correctly the DFT has identified these two frequency components, right. Rest of the components are shown to have 0 magnitude, because they are which means that they are not present in the original signal, which is true, right. Also the magnitude of this component, you can see we have frequency component at 5 Hz and also at minus 5 Hz, and the magnitude is 2, right, 2, which is half of the actual magnitude which was 4, the amplitude was 4, but in the complex DFT we get the components at plus minus frequency with half the amplitude. Same thing is true with the 10 Hz component whose true magnitude was 12, okay. Let us go to next figure. So figure 4, it is now single sided DFT. Now this is from 0 Hz to 15 Hz, correct, and you can see now it shows a component at 5 hertz of amplitude 4, which exactly matches with the given signal, and then there is another component at 10 hertz of amplitude 12, which again matches with the component which was there in the given signal. So this clearly shows that our program is working and giving the correct estimate of the frequency components which are present in the signal in terms of their frequencies and amplitude. Okay. So I think this solves our example number 1. Let us now try to see the code for example number 4. Let me open that code, example FFT. So this is the code which I have written for the second example. Now in this example, the only change is that instead of using our own code for DFT, we are going to use the MATLAB inbuilt command for FFT. So this initial part is all same, you can see here, it is all I am defining the time and Fs, and then finding time frequency domain parameters, all that thing is done. I am discretizing the signal as was done in example 3, and now after this is the change. Now we are finding FFT DFT using the MATLAB FFT command, right. And what is the command? The command is simply FFT, right. And what are the inputs to this command? The input to this command on the right hand side, as you can see, first variable is the time vector, is the vector of the samples of the signal x, right, a vector of the samples of the signal x, and n tells the number of samples in the signal, right. What is the, but that again is also can be determined from x itself. So and then on the left hand side we will get x k, okay, which is the magnitude of the which is the the component of the different magnitude of, not magnitude but the frequency components themselves, right. So that is what we get, okay, and they are in general complex. And also the MATLAB gives you the frequency components, it is a complex frequency components and two-sided DFT components, and those components are multiplied by n, right. So that is why we need to estimate the correct value of the components by dividing the xk by n, okay. So it gives xk with a multiplication factor n. So that is why we are dividing it by n in order to get the correct values of the magnitude of the components. So this is also an important step. So we get xk is equal to xk by n. Now after this, this is same, we had developed the vector of complex frequencies, but there is one difference in the MATLAB's FFT command with the code we had written down. Our code frequency components started from negative side and went up to the positive side, but in the FFT MATLAB's FFT command, what output it gives? It gives the first first half components as the positive components, and after that it stacks the negative components, correct. So it has first the components from 0, starting from 0 going up to n by 2, and then it stacks the negative components after that. So that is why we have to make that adjustment and then properly interpret those lines when we plot the figures. So that is why you can see this vector is same as I had done in example 3, but now I am finding I am trying to establish the correct frequency vector for plotting the output of the MATLAB FFT command. So you can see here I am defining a new variable f vac complex FFT and defining the first n components as the last n components of our vector, and then the next n component half components, right. Here you can see next half of components as the first half components of the our vector which we had defined. So this is an adjustment for plotting the frequency vector correctly. And then also we are converting now the FFT double sided, we have FFT to single sided. So in the MATLAB single sided FFT we have to just take the first half component straight away, we can take that, right, and take twice of that as I have done here, right. So this gives you yk gives you the single sided FFT, and then we are setting the again the real frequency vector. Now so this was basically the change with respect to the previous program. Now after this, for drawing figures, that is basically the same part, the code is same as I used in the first example for DFT. You can see this is the same code, like same code, okay. Appropriate variables are used, first plot continuous signal, then discrete signal, then two sided FFT and one sided FFT, right. So this completes our code for finding DFT using MATLAB FFT command. Let us run this. Let me press run. So it is busy, it is running and now plotting the figures and it has done the job. So you can see this the same signal as we had got overlay of continuous and discrete signal, and then we have this discrete time signal as we got in the example 3. This is now the two-sided DFT obtained using FFT command, and you can see it is exactly same as we got using our own code, right. So this validates our code also, right. So it's same, results are same, they need not be explained anymore. And this is the single sided FFT, which again exactly same as what we got with our code, and this also correctly predicts the frequency and amplitude of the frequency components that were there in the given signal. Okay. So this completes the solution of example 4 as well, right. So I think in this way we have today solved 4 examples, 2 numerical examples and 2 MATLAB code based examples, right. And now we can stop here. Dhanyavad. Thank you.